Hello, today we are going to continue our series on proof by mathematical induction. In the previous exercises, I have covered the proof by mathematical induction which involves divisibility, also the case which involves matrices, and recently in the previous video, I did the case which involves the nth derivative of a function. Today, we'll be looking at the case which involves series, especially series that is written in sigma notation. The question says, prove by induction that for n belonging to the set of positive integers, summation from r equals 1 to n of r times 2 to the r equals 2 into 1 plus n minus 1 times 2 to the n. So this presentation is typical of questions that come very often in the exam, be it in advanced level pure mathematics or in further pure mathematics. Generally, when you see such a question which is involving proof by induction, involving a series, especially the one having the sigma notation, you have to first interpret this function of r, the function that follows immediately after the sigma notation. It is usually a function of r and is called the summand, which actually is the general term. We can call it UR. It is the function that generates the terms of the series, whereas the function on the right hand side, which is usually a function of n, is the function that generates the sum of the first n terms of the series. It is important to get that interpretation before you go into the proof. So for the base case, which occurs when n equals 1, we would be seeking to show that u1 equals s1. That means r equals 1, it will be generating the first term, and when n equals 1, it will be generating the sum of the first term, which is simply the first term. So when r equals 1 in the summand or the general term, we would have u1 equals 1 into 2 to the power 1, which is equal to 2, and when n equals 1, substituting in the right hand side, we'll get the sum of the first term, which should be 2 into 1 plus 1 minus 1 times 2 to the 1, which gives you 2 into 1 plus 0, which is 2. So we then have that the first term is equal to the sum of the first term, which is equal to 2, and so the formula is true for the case where n equals 1. In the hypothesis step, we would assume that the formula is true for n equals k. So to get the statement that we'll write in the hypothesis step, we just go to the formula and replace every n by k. So I get summation from r equals 1 to k of r times 2 to the r equals 2 into 1 plus k minus 1 times 2 to the k. So from here now, I have to go to the inductive step where I need to prove that the statement is true for n equals k plus 1. So for n equals k plus 1, I'll have summation from r equals 1 to k plus 1 of the summand, which is r times 2 to the r, and this should be equal to. Now we have to be careful in this case. Remember, again, like in the other previous cases, the inductive step has to be proven true by making use of the statement that is obtained in the hypothesis step. So for us to use the statement that we have obtained here in the hypothesis step, I will need to be strategic in that I will break that sum down into the summation from r equals 1 to k first, because the summation from r equals 1 to k is in the hypothesis step. That is why I'm using summation from r equals 1 to k. I could have still used summation from r equals 1 to any other integer lower than k plus 1, but I'm preferring k because the summation from r equals 1 to k is involved in the hypothesis step and will then help me to arrive the proof in the inductive step. So I will have to consider first the summation from r equals 1 to k of the summand, which is r times 2 to the r. Then I add the k plus 1 term to it, which is uk plus 1. That would give the same thing as the summation from r equals 1 to k plus 1 of the summand. To better understand how this statement has been arrived at, let us consider the case where I have a simple sequence with the first, second, third, fourth, and fifth terms. If I want to get the sum of all 5 terms, I may start by first adding the sum of the first 4 terms. So that is summation from r equals 1 to 4 of whatever function is generating the terms. And then when I add now the 5th term, that means u5, to that sum of the first 4, I will now get the sum of the first 5 terms. So you can see that this resembles what we have just done in the general case in the beginning of our inductive step. That is always the procedure you would follow in the inductive step each time you have proof by mathematical induction, which involves a series given in sigma notation. In the next step, we need to have an idea of what the summation from r equals 1 to k plus 1 of the summand would look like. So the statement again that we are seeking to prove that it is true, summation from r equals 1 to n of r times 2 to the r equals 2 into 1 plus n minus 1 times 2 to the n. So I would need to show, that is the requirement, so that I have an idea of what I will be proving. I will need to show that summation from r equals 1 to k plus 1 of r times 2 to the r would be equal to 2 into 1 plus, I would replace every n by k plus 1. So k plus 1 minus 1 would just be k, then times 2 to the n, and n is replaced by k plus 1. So this is the statement that I'll be seeking to prove in this inductive step. So going back to the statement I started with, I would have summation from r equals 1 to k plus 1 of r times 2 to the r equals, from here now I need to replace this part of the statement by the right hand side of the hypothesis step. As I said, it needs to participate in the proof of the statement in the inductive step. So bringing the statement, then I should have 2 into 1 plus k minus 1 times 2 to the k plus uk plus 1. And to have uk plus 1, I simply come to the summand and replace every r by k plus 1, so that I get k plus 1 times 2 to the k plus 1. In the next step, we would have to be very strategic in order to get the proof. That is why it is important to always write the requirement. We wrote this requirement that it should guide us in order to move from this complicated statement into that one, so that we can be able to conclude that the statement is true for the case where n equals k plus 1. So I will begin by factorizing 2 from the right hand side of that statement. It has 2 terms, this one and this one. So when I factorize 2, I will need to divide each of those terms by 2 to know what I will write inside the bracket. So this first term divided by 2 will just give us 1 plus k minus 1 times 2 to the k, and then plus k plus 1 times 2 to the k plus 1 divided by 2. When you divide 2 to the k plus 1 by 2, you get 2 to the k plus 1 minus 1. So we'll just be left with k plus 1 times 2 to the k in that bracket. So from here I will have 2 into, I will simply expand everything inside the bracket there and then see how it simplifies. So I have 1 plus 2 to the k times k will be k times 2 to the k. 2 to the k times negative 1 will be negative 2 to the k. 2 to the k times k will be plus k times 2 to the k. 2 to the k times 1 will be plus 2 to the k. This will be equal to 2 into 1 plus, now there is negative 2 to the k plus 2 to the k, they will cancel out. Then k times 2 to the k plus k times 2 to the k would give us 2k times 2 to the k. And finally we have 2 into 1 plus. In our statement we had k times 2 to the k plus 1. So this 2 times 2 to the k will now give k times 2 to the k plus 1. So which is true for n equals k plus 1. So we can then conclude that statement is true for all n elements of a set of positive integers.